the second half of the day. And today's speaker is Souvik Bera, who is finishing up his Ph.D. at IISC Science, and we'll be talking about epsilon expansion of multivariate hypergeometric functions in terms of multiple solutions. So,
we have to use it right now.
You have to use it. Now, follow little bit above, little bit above. Now,
Hello.
Slide changer is this beside the project.
Thank you everyone for being here, and thank you Professor Lahiri for hosting me. So today I'll be talking about epsilon expansion of multivariate hypergeometric functions in terms of polylogarithms. So the overview is the following. I'll start with some motivations, and then before going to the algorithm, I have to define some of the functions and their properties. And finally, I'll talk about the mathematical implementation of the algorithm. Okay, so to start with, this is the big picture. So our goal is to predict some of the physical quantities in a scattering process, and we end up with calculating lots of Feynman integrals. Those will be containing some Lorentz structure or color factor. So that has to be decomposed first, and finally all you have is lots of scalar Feynman integrals to be evaluated. So there are different methods to do the evaluation, and these are the 4 such cases where you express this integral in terms of hypergeometric functions that I will define in next slides. So what are those? The most popular is the Milling-Barnes method, and there are method of brackets and then negative dimension. And recently this approach is called GKZ or a hypergeometric approach, and this got some popularity recently. And we have as a group built a package that's called FineGKZ in Mathematica that does the thing for you. That means it takes an integral and it gives you the hypergeometric function representation. So once you have that hypergeometric function representation, so those will be valid in a certain domain because those are series. Then you may wish to find the analytic continuations because you want to evaluate that function at a point that is beyond this defining region of convergence. So in order to do that, there are also different methods to analytically continue that function. And we have also developed one package called Olson.wl, which is based on the method of Olson, to find the analytic continuation. And finally, once you find your suitable analytic continuations, then you wish to perform a series expansion of that integral in terms of dimension. So this is the topic of the talk today. So I'm going to present this package multi-hypex that takes a hypergeometric function and perform its series expansion in epsilon. So to let us follow an example. So we are considering this one loop 2-point function, that is Passarino-Feldman V0 function, and that is evaluated using this negative dimension method to the hypergeometric function that is called F4, apple F4. So what I mean is that integral is a sum of some terms, and each of this term will have this apple F4 in it. There will be some coefficients as well. So for coefficient 1, this apple F4, plus coefficient 2, this apple F4, and so on. So the point to note is the dimension parameter d, which usually written as 4 minus 2 epsilon, appears in the what you call is Pochhammer parameters of this function, and the ratio of the scales involved in the integral, that is the mass of the propagator, and the external momentum appears as a variable here. So this is essentially the state 1. So that is, given an integral, we write it as a hypergeometric function. So this integral is written in terms of appellation.
Do you have an expression for, in terms of integrals of this?
Yeah, so integral, no, I do not present an integral representation of that, but I have the series expression here. But if you want, do you want this integral of one?
That's the Pasadena-Feldman, right?
Yes.
So that requires this F4.
Yes.
Right? So Pasadena-Feldman is the sum of right?
Yeah.
So do you have an expression? I mean, otherwise F4 is just a simple
black box.
Yeah, I'll just
This is
define it
simple.
in the next slides. So again, take another example of one loop 3-point function. These are expressed in terms of appel F2, and consider another example of 2-point function with 2 loops with 3 different masses. This can be expressed as Lauricella FC. So the point from this slide is that you express that integral in terms of hypergeometry. So in the next slides, I will define what these functions explicitly look like. Before doing that, we need some notation. So we all know about this gamma function, but in the study of hypergeometric functions, the ratio of 2 gamma functions which appears mostly, these are called Pochhammer sigmas. These are the two argument x and n. So if n is an integer, it is essentially a product of some terms. So these are basically generalizations of our well-known
X is what?
X is a complex number apart from non-negative integers of 0.
Okay.
Because otherwise at some point it will be 0. Okay, now if you take 3 such parameters A, B, C, which are in general complex numbers apart from negative integers, and a variable x, and arrange that in this fashion, where n is the summation index that runs from 0 to infinity. This is essentially the well-known Gauss 2f form. It's valid for mod of x is less than 1. The first few terms look like this: 1 plus something plus this. So at this point, one has to note that A, B, C are generic values. That means these do not take such values where either the series terminates or it diverges. For example,
ABC are real?
ABC are general complex values. Apart from these things, that C cannot be 0 or negative integer because this will be infinity. Other A and B also cannot be 0 or negative integers because at some point it will terminate. So this will not be a series anymore. So there are generalization of that. This is called PFP minus 1, where you introduce new Pochhammer parameters in the upper and lower, in the numerator and denominator. But the variable remains 1. That is, and it's also valid for mod of z is less than 1. Now, mathematician has studied the generalized hypergeometric functions in the sense that they have now taken 2 variables x and y. And Apple is the first who did that. There are 4 Apple functions, f1, 2, 3, 4, and it takes again some Pochhammer parameters like a, b1, b2, b3, and 2 summation and 2 variables. Note that these are not exactly the product of 2 f1s because this is a non-trivial mixing of 2 summation indexes. And when you write this this series expression of a function, that you must also mention the domain of convergence. So this series is only valid when this condition is satisfied. Similarly, Apple F2 and Apple F3 and Apple F4. To give a flavor of how this domain of convergence looks like, so I just plotted the domain of convergence of F2, that is mod of x plus mod of y is less than 1. That looks like this this box in real x1, x2 plane. So that means when you are inside that that YOLO region, you can use this series expression to evaluate the value of the function. But what would happen if you want to evaluate that at the breakpoint? So that means this series representation will not be valid. So you have to perform some analytic continuity. in one of our project, we find all the analytic, many analytic contributions such that all the real XY plane is known. So I have taken one such that is plotted in blue. So this is how you find the analytic contribution. So that means we are at step 2. So we find the defining series and then how to find the proper analytic contribution. Okay. Now the next thing is all about the epsilon x function.
When you say analytic continuation, you actually mean that you can find the value of the
Yes. So you have to find another series representation that will be that has a support at that point. So if you can find another one which will look some different, but different from this one, or a mirror image of this with y equals to minus x9, and in this way you cover the whole space, and there should be overlapping.
But the given representation does not converge, right?
Yes, because yes, it is greater than 1. So x is 4 and y is 2, and if you put x is 2, x is 4, y is 2, at some point it will be that.
Right.
But in this expression, you can find another series representation where argument would be 1 by x and 1 by y.
Yeah, but then the question is, how do you define the function so that it's well defined everywhere?
Yeah, in the overlapping patches, you have to match the value of two different values.
Yeah, but how do you define the function? How is the function?
Yeah, and in this
The definition is not by this series, right? Not by this.
yeah, at this region, this is the definition, and we find another patch that is overlapping with this, and that expression should give the same value as the defining expression.
No, that is okay. What I'm saying is that, if you want to define something in transfer series, then you cannot define it beyond the validity of this.
Right. Yeah.
So there should be some other definition which reduces to the different series in different regions. Some top definition which reduces series expression.
It indeed has some
That's
integral
right. Yeah,
representation,
exactly.
but I doubt that representation will
that may not also converge.
Yeah, that may not.
Okay.
Okay. So again, we need some more definitions of hypergeometric functions again. So there are Horn functions G1 to 3 and H1 to H5. One of them just I have written here, just to show the complexity. The Pochhammer is in minus n here. In the previous cases, we have n plus n. So H2 is much more difficult to handle compared to the other Appel functions. So these 4 Appel functions in the previous slide and the 10 Horn functions form the complete set of ordered to multiple hypergeometric. And some of them are also related to each other. So this study of this relations is called the transformation theory of hypergeometric functions. And then there are higher order series which are called Capelli-Fourier functions. Again, you put lots of Pochhammer in numerator or denominator, and actually there are infinite numbers of them. I have taken this because this will come in the latest slide. And the Lauricella function that is 3 variable is defined in this way. Note that this is the function in which the sunset is expressed in this slide. So now there are some study from the literature where they have taken the series representation of a hypergeometric function to find the series expansion. Otherwise, you can take integral or Marin-Burns representation. Also, these functions are the solution of differential equations that you may take. Some complicated study of coaction can be performed. So there are packages also that can find the series expansion of this function. One of them is HYPEX. It can only do FP minus 1 type function, and then X sum or nested sum can do some Appel functions. And this NumPX is the numerical. NumPX is for numerical expansion.
Souvik?
Yes.
Just to want to clarify. So you do not use anything about Marin-Burns representation theory. That is a standard theory that we use.
Yes.
And I have a curiosity that Pochhammer these symbols
Yes.
are also heavily used in mock zeta function, Ramanujan
Yeah.
zeta function.
Yeah.
So you didn't try those things. Did you try?
No, I have not, because
It really didn't need it.
yeah, we do not see that in primary integral calculus.
Some different calculation.
From okay, but
It can be done.
it can be done.
Yeah, maybe that can also be represented in some sort of hypergeometric function.
Sure, because,
I
because
do
his
not-
Rahman's book is there.
Yes. Okay, so before we move on to the algorithm, so there are two things that we need to know about this hypergeometric function. One of them is these are the solutions of differential equation, because that's how we were taught in class. Because we start with an ODE and try to find the solution of that ODE continuous method. But what we need is the other way around. We start with a series representation here, 2f1, and we want to find its associated ordinary differential equation. To do that, so there is a general procedure. So whatever is there except the x to the power n, you write it as an and take the successive ratio of two terms and simplify that. Call the numerator as g of n and denominator as h of n, which a 2f1 looks like this. And then you construct this operator L, where h as a function of theta, then promote this n, the summation index to this operator x. And it is guaranteed that this operator L will annihilate this function. That means this is the ordinary differential equation of 2f. It turns out that this procedure can be generalized to more than one variable. So now we have a R variable series written in very compact way. Again, we write all the things as a of m and x to the power n. Then we can find R such ratios where again m is a vector here and E is the unit vector with ith entry. You can find R such ratios. So in more than one variable, we will have partial differential equation rather than ordinary differential equation, and these operators will annihilate this function, constructed in the same way as in the previous case.
What is x to the power m vector?
Yeah, x to the power x1 to the power m1 times x2 to the power m2.
I see.
Okay, so yeah, this is one property we need. And the second property we need, that we all know this Gauss 2f1 has contiguous relations. That means 2f1 with ABC is related to 2f1 with ABC plus 1. There's also a procedure to find such contiguous relations. And we only need the procedure where you can generate such relations. That can be generated by constructing some differential operator again. So for example, this operator, again theta is the Euler theta operator. When acts on this Gauss 2f1 with a, b, c plus 1, it reduces the Pokémon in the C by 1 unit. How? Let's do that. So we apply that operator here, and this is essentially some gamma function manipulation. So if you do that, you essentially get the 2f1 again. So this procedure, if you want to apply for more than one time, for example, you wish to reduce the denominator, the Pokémon parameter in the denominator by 2 units, you do apply this operator twice. And when this operator has a derivative which is more than order 2, then what you can do is you can take a quotient with respect to the ODE. That means every operator of this form will have this form, that is something minus something times this theta operator, not more than theta square or anything. So it turns out that this procedure can also be generalized to more than one variables. Again, we write the definition of the hypergeometric function in a compact form, but this time to form the step down operator, we need this matrix new. So again, this new matrix will be multiplied by a theta vector, and that differential operator will, when acts on this function, will reduce the Pokemon in the denominator by 1 unit. So again, if you need to reduce this Pokemon multiple times, you multiply all those operators and take the quotient with respect to all the annihilators of this function. So this is how you construct the step down operator. So now we are ready to find ready for an example of a series expansion of 2f1. For example, this 2f1 ABC. Again, I have written the definition just to show you that when C is a non-negative integer, at some point it will be divergent, and A and B is also a non-negative integer. So what we want is to expand the function 2f1 with 1 epsilon plus 1 x in terms of series in epsilon. So the first thing to do is, if you put naively epsilon goes to 0, you can get the leading term, because let's do that. So if you put epsilon goes to 0, that means 1m will cancel out, and this will also cancel out with the m factorial. So what we have essentially is x to the power m, and sum over m goes to m to sum over m, that is from 0 to infinity, and that simplifies to 1 by x. This can be done because this C can not be a non-negative integer, but in this case, this is plus 1, is a positive integer. We can do that. Now we consider another function, but instead of epsilon plus 1, we have epsilon minus 1 here, but everything else is same. 1 epsilon plus 1 previously, and now 1 epsilon minus 1. In this case, we cannot directly put epsilon goes to 0, because at some point minus 1 to the power, Pokemon minus 1 m will be 0. So how do you expand A1? So the strategy I have taken is, so you first find a relation that first find a differential operator that will relate the problematic hypergeometric function with a simplified hypergeometric function. In this case, so in previous slide we have found this operator explicitly, and if we act that operator on the series expansion of this in the leading term, so we find the leading term of the series expansion of this complicated function that we previously could not find. So this is the overall strategy. So when you encounter a function that has singularity because of some Pokemon goes to 0, then you relate that to a simplified function by a differential operator. Find the series expansion of the simplified function first, and then we act that operator on the series expansion. So that is the overall strategy. Okay, so before doing that, we need to mention that when the Pokemon parameter is of the form b0 plus b1 epsilon, and b0 is negative or 0 integer, 0 or negative integer, so we'll call that a singular Pokemon parameter, because those are the problematic cases. If one or more lower Pokemon parameters of the multiple hypergeometric function is singular, then epsilon expansion of that function would be Laurent. Otherwise, it is stable. So we first distinguish the type of expansion. Now here comes the steps of the algorithm. So at first step, we check if the lower Pokemon parameters of the given functions are singular or not by noticing this parameter b0 is 0 or negative integer. If it is non-singular, that means it can be performed that can be expanded in Taylor series by taking successive derivatives and then putting epsilon goes to 0 at the end. And if it is singular, if some of the lower Pokemon parameters are singular, then we replace that singular Pokemon parameter by a regular one by simply replacing b0 by 1. So this is not singular anymore, because b0 is now a positive integer, and we have to find such operator, step down operator, where the new function g is related to the old function f by the action of this operator. And then g of epsilon can be expanded in Taylor series, and we can also expand this operator in series. And then we act this operator in term by term and find the series.
What are HI?
HI is the coefficient of epsilon expansion of h.
No, but H is an operator. Right?
Yes.
So
So, but
HI should be also operator.
yes, it's
So
also.
you need an infinite number of operators.
It depends on how many terms you need on the left hand side. You need so 2 terms in the
Yeah, but I mean, what operators should they be?
yeah. So let's look at this. So this is what we have an example of each operator.
Yes.
This is not expanded form, but if you expand in series, it starts with 1 by epsilon plus higher order of epsilon. So all this operator does is it takes out the divergent part in it, right? So the 1 by epsilon part, and the regular part is there in the series.
But theta is a differential operator.
Yes, theta is a differential.
So
XTS, huh?
XDX.
So are you going to get higher powers of theta?
No,
Okay.
it's already
That's a big question. So HI is simply different coefficients of theta.
yes.
But you will end. I mean that series will end. Why will you get more than 2 or 3 HI?
It will not end. Will not. If you expand it 1 by
I see you are going to have epsilon power. Alright.
okay, so yeah, so another example. So this time we take again 2f1 with the parameters epsilon minus epsilon epsilon minus 1. But note that this lower Pokémon parameter is epsilon minus 1. That's a singular parameter. So this will have problems while expanding this function in epsilon. So instead of expanding it directly, we form an associated function a2 that has epsilon plus 1 in the denominator, except that everything is fine, everything is same. So this function has Taylor series expansion, and this is how we find the function in the series form. So we start with 1 plus epsilon square, and these are the 3f2 function, and this is the KDA function that I defined in the first slides. And note that this is a double variable function. We started with one variable, one summation index, and it's now have 2 summation index, but the number of variables is same, and it is x. And this is also be valid for mod of x is less than 1. So the domain of convergence in the left hand side and the right hand side should be same. Okay, so this is the KDA function that I mentioned. So again, we find the differential operator using the prescription and find its series expansion. And this time it starts with 1 by epsilon, and so it goes so on. And you may truncate it at some point by the requirement of how many terms you need in the final answer. So by applying h on the Taylor expansion of this function, you can get the series expansion of a1. So we applied this operator h in this to find the series expansion of a1 as so this is the an example of the algorithm. And it turns out that this KDA functions are complicated to find, evaluate beyond their domain of convergence, and higher order terms will have hypergeometric functions with more summation indices. That also takes too much time to run the sum. So instead, we could do is we could slightly modify the algorithm and express all these complicated functions in terms of what we call polynomial. So that is what is done in the package. So the previous method that I described had some advantages, like it can be the expansion can be performed around any values of Pokémon parameter. But the disadvantages are it is only valid for a certain domain of convergence, and higher order terms will have higher summation fold functions, which are really slow for numerical evaluation. So instead, if we restrict ourselves to integer values of Pokemon parameters, so we could simplify all this complicated expression in terms of MPLs. So MPLs are defined, or multiple polylogarithms are defined in this way. These are iterative integrals that starts with g of z is equal to 1 with no other vector a, and a is called the weight vector, and its length, yeah, a is called the weight vector. These are all related to the well-known logarithms or its generalization called polylogarithms. And this is where this is what we are going to expand the function of finally. Okay, so to bring to change the function, to test the procedure a little bit, we first bring the ODE of F1 to something called Pfaffian form. Is we construct this vector g, that is the function as the first element and its derivative as the second element. And if you apply the derivative operator on that, you can find the matrix differential equation as a Pfaffian system with the integrability condition there. And it turns out that for multivariable hypergeometric function, you can do the same, but the length of g will be different for different functions. In this case, it is 2.
Is ONG just the matrix product?
Yes. And in this case, it is 2, but in other cases, it depends on the holonomic rank of the partial differential equations you have, and that can be calculated using Grobner basis calculation. So once you have that Pfaffian system, for example, this A2, we have this as a matrix in the right hand side. That means the differential equation looks like d of this vector is equal to epsilon times g again. So it turns out that one can perform a suitable transformation T. That means we change the basis from G to G prime by a matrix T that is given by this, such that this Pfaffian system can be brought to a something called canonical system where epsilon is now factorized out of this matrix omega. So by the change of basis, we do this, and this omega prime is now looks like this. And now we need to find the solution of the differential equation order by order with a proper boundary condition. To find the boundary condition, we note that this 2f1 starts with 1 plus something something. So we can choose x to be 0. So 2f1 at x equal to 0 is always 1. So its derivative with respect to x and can also be evaluated at x equal to 0, and which always gives 0. So that means we have a boundary condition that the vector g at x equal to 0 is 1, 0. So now we find the solution of this Pfaffian system with the boundary condition here, and it turns out that A2, this function has series expansion in terms of polylogs as 1 minus epsilon squared times polylog 2 and so on. For comparison, I have posted the previous expansion where this all complicated looking 3f2 are reduced to polylog 2, and all the KDFs and combination of KDF and 3f2 are now simplified to polylog 3 and polylog 1. So this is the simplification of the final answer. So this algorithm is now realized as a mathematical package. It's called multi-hypex, and it can perform series expansion of PFP minus 1 and the Abel functions and Horn functions and certain KDF functions. It can also find some series expansion of Lauricella functions of this set. And apart from Abel F1, 2, 3, and H2, all the Horn functions are evaluated using their transformation theory to Abel F2 or this 4 functions. But the thing is, Abel F4 and H1 is not possible to expand without restricting certain parameters because these are too complicated to expand in series. And the package is package depends on 4 other dependencies. These are well established package from the literature. Some of them is called holonomic function. This is used to find the PDE associated with the hypergeometric function and to bring it to the Papian system. And then the step up-down operators are already implemented in hyperdial packages. And to bring the Papian system to the canonical form, we use Canonica. And to integrate and manipulate polylogarithms, we use polylog tools. So this is how a Mathematica input-output will look of the package. So series expand is the main package, main command. So it takes the argument as follows. So f1 is the head of the function. That means you are expanding apple f1 with this set of common parameters 1 minus epsilon minus epsilon minus 2 epsilon, and the variables are x and y as before. And e is the variable that you want to find its scalar expansion of, and 4 is the maximum number you want to truncate this series. So G are the same as the polylogarithm, which is this G. Finally, we expand this apple f1 with this set of parameters as this.
So that expression for polynomial.
Yeah.
So we want to n and so n. Okay. But here you have only G is 2 values, right?
Yes, G with 2 values. And it depends on how what are the order. So in first order it is G1x, and in the say
I
it's
see.
fourth order.
Okay.
So this command can also take input in a slightly defined way when you have to explicitly take the series expansion series definition of apple f1 here, and it also means that you have to define the summation indices m and n here. So this input will also give the same output as above, but this is done because we also need to expand some of the capital effective functions. Okay, so it has yeah, the package is now in archive is under review, and it has some limitations. So the package can find the series expansion of the series around the integers values of Pokemon parameters, not the half integers, because this will need some more complicated change of transformation at the Papian system level. So this has not been done in the dependent package Canonica, so we cannot do that. And it can handle MPLs, that's multiple polylogarithms, up to 6 weight. That's why you have to restrict the maximum highest power of epsilon to be epsilon 6. And it takes sometimes to run for a 3-variable hypergeometry because the dependent package is taking too much time to evaluate. Okay, so this is what I have.
So can you compare the results that you find with the results found in other methods?
Yes. So the other method what we use is direct derivative.
Right.
So we put that expression in Mathematica, take the derivative, and take epsilon goes to 0, provided that it's not causing any warning or anything. Then we run it very. We check that up to 30 decimal points. It's matching.
For small epsilon, or epsilon equals
No,
epsilon what size? 0.1, 0.01?
no, epsilon is taken to 0 after taking the derivative. So we are just expanding in series by taking the derivative, and then each coefficient we have to take epsilon goes to 0 at the end. We are doing this.
But shouldn't the match for non-zero values of epsilon also?
Yes, it should also.
Can you check? Did you
Yes,
check that?
yes, but very slow value, very
Very small.
low value. Yes.
0.1 or 0.01 maybe.
We take it 10 to the minus 10.
Achha.
So it turns out that that value is absolutely matching this GPLs up to 30 decimal points.
Are the polylogarithms also, do they also have a radius of convergence?
Yeah.
Yeah.
By definition, it
By
has.
definition, yes.
But the numerical package to evaluate that already includes all its analytical. But you do not have to care about analytical when you perform numerical.
But at the borders also,
Yeah, they have provided it.
Because they have an integral representation, right?
Yes.
they do, but mathematical may not be able to do that as well.
Yeah, mathematical may not be able to do that.
You don't know that.
And it's a good work, very good work.
Thank you so much.
I have just one comment.
Yes.
Do you, I think I know how to express multiple zeta functions in terms of polylogarithm.
Yes.
So I believe your
You
project
have to do that.
can be extended to the multiple zeta functions.
Yes. Yes.
Of course, there is a limitation because multiple zeta function has this some kind of symmetry you have to use. We use shuttle
Yes.
product. But here also, I think that would
Yes.
work. Maybe you finished your thesis. Have you finished? Have you written the thesis?
No, I'm writing it.
So I may like to have some copy of your thesis because it would be interesting to
Yeah.
understand.
Thank you very much. I'll see you. Definitely.
I just wanted to say a word if I have the permission. First of all, hello everybody.
Yeah.
Yeah.
Is that-
So,
Yeah.
this is Anant here. I wanted to say hello and show you my face, but the camera is not working on my laptop. So,
Here, you don't
I just
know.
wanted to respond to one or two things. First of all, the main motivation for this, of course, for us as physicists comes as evaluations of Feynman integrals. So we were led into all these investigations of hypergeometric functions of many variables and so on. And we found during the course of the last 3 or 4 years that many of the inbuilt functions of Mathematica and all are really inadequate. Also, Maple also has some. So we started out by trying to compare and understand the situation, and then eventually, of course, we were also driven to this needs of this epsilon expansion, which is really needed in Feynman integral calculus for dimensional regularization. And there was a question about Mellin-Barnes. Of course, Mellin-Barnes techniques are either implicit or related to all these investigations. Hypergeometric function theory always has, backbone of Mellin-Barnes investigations. There was also a comment about mock modular forms. They are also related, but for the moment, I think the people in the industry are just learning about these modular arithmetic and mock theta functions and all these things. And there are basically classes of integrals where you always are guaranteed to get multiple polylogarithms, especially at the one loop level. And then we already find at the two loop level with where the momentum routing is somehow non-trivial, then immediately you are led into a situation where there are elliptic generalizations of these polylogarithms and so on. So it's actually a rather young field. The last only about 7 or 8 years, people have started looking at these things. Weinzierl, in his book of 900 pages, he has a few words about these elliptic functions and iterated integrals. So this is all like really, cutting edge research that's going on. Often what happens is that people eventually appeal to some numerical evaluation. So our interest has been in trying to push analytical methods as hard as possible. And I don't know, maybe Amitabh or others can comment on this. What Souvik has demonstrated with his annihilator is that it actually seems to respect some kind of a Grassmannian algebra. Maybe there are some properties of such algebras which can be exploited to make these systems more interesting. I don't know. It's just a comment or a question that I have for you.
I don't know.
I think that it should be going back to a certain kind of work done by the Japanese school, because this holonomic and this PDE connection with multiple hypergeometric functions. There's at some stage Kashiwara-san, Jimbo Miwa Kashiwara, they worked on together. Actually, I am interested about that, and I those things you cannot able to calculate it out. Now there is a lot more thing to do about related to applied things also.
May I know who is addressing us right now? I don't know who's speaking. I see. Hi. Okay.
So that is a very good thing, as well as this kind of things also very. I'm sure that when I started looking at the multiple zeta functions, and it was very difficult. And in fact, my supervisor called Don Zagier, and Don actually gave me some really concrete values for the lower values, lower dimensions. You know, as you said that up to 6 you can do that.
Yes.
It is really a problematic. After that, you know, because there is a lot of shuffle products, all sorts of problem complications coming out. So I want to know a little bit more from this. I want to learn from you.
Rosmanians, I don't see how.
Because it all comes from that soliton equation, soliton solutions, everything would come into the play.
But you are indeed correct that this method of getting that differential operator is due to Takayama, which is a Japanese.
Takayama is actually Takayama. Also, I was curious, you know, that you have a first order differential operator. Huh?
Yeah.
See, I have also, we call it chain. Chain, you know, first order differential operator. For example, you know, Riccati operator. You would take the successive of this, just like that, you know. I can talk about in terms of algebraic geometry, but then you get a second order construction. But what did you do? You actually cutting lowered the dimensions of the operator by action.
Yeah.
But opposite things are also very interesting. Successive thing that also helps you to construct certain things. Anyway, I'm interested, very much interested in your work. Very good.
Thank you very much.
Excellent.
Any other question? Okay. Let's thank Souvik again.
Thank you, Souvik. Very good. Well done. Well done. So when you finish, you